Hello friends, here in this video we will see a problem on double integration method. Here is the question. Determine the deflection at points B, C and D in the beam as shown in below. Here the figure is given. The beam is circular in cross section having diameter of 200 mm. Take capital E, Young's modulus 200 GPa. Now this is the question we have. I'll write the data. Now the diameter of the beam is given, it is 200 mm, so that becomes 0.2 meter. Young's modulus is 200 GPa, which we can convert this, so it becomes 200 into 10 raised to 6 kilonewton per meter square. Now the question is, we have to find deflections. Deflection is denoted by Y. At points B, C and D, we have to calculate the deflections. And now this is the question we have. So in order to solve this question, we are going to use the double integration method. And for that, the first thing is we should know the beam reactions. So here what I'll do, in the solution part, I'll draw the diagram of the beam again. So here we have the solution. In this, drawing the diagram of the beam again. I'll mark the distances here. Now, this is the beam which is given in the problem. The first thing is we should calculate the reactions, that is how much will be reaction at A and reaction at B respectively. So here I'll say that considering the given beam under equilibrium, here I'll write down first summation of Fy is equal to 0, where upward forces are positive and downward forces negative. So we have Ra plus Rb, both are upward, minus 20, minus 30, then 10 into 2, because I have to convert the UDL into point load, so it is 10 into 2, that becomes 20 and acting in the downward direction, so negative, is equal to 0. So therefore Ra plus Rb will be equal to 70, and I'll keep this as the first equation. Now using the second condition of equilibrium, I'll calculate the moment of all forces at point B, because I want Ra first. So summation of moments of all forces at point B is equal to 0. Here clockwise moment will be positive and anti-clockwise moment will be negative. So if we see, Ra is producing clockwise moment, so Ra into the total distance, which is 5, Ra into 5, then this 20 is producing anti-clockwise moment, so it is 20 into 4, so here I'll write down minus 20 into 4. Next, this point load, it is also producing anti-clockwise moment, so minus 30 into 1. Then we have UDL, so this point load will be 20, that is 10 into 2, 20, and it will be acting at half of 2, that is 1 meter. So 1 plus 1 plus 1, that gives us 3 meter distance from point B up to the point load of this UDL. So 10 into 2, that is the point load, into the distance is 3, and it produces anti-clockwise moment, so negative sign. It's equal to 0. After the calculation here, I'll get my Ra value as it is 34 kilonewton. Now once we get Ra, I'll say that therefore put Ra is equal to 34 kilonewton in equation 1. So Rb will be 70 minus 34 and that is 36 kilonewton. So I have found out the support reactions. Now after getting the support reactions, in this problem they have given us the diameter of the beam. So from that I'll calculate the moment of inertia. Therefore the next step is Mi of given beam. Since the given beam is circular in cross section, its diameter is given, that is d is equal to 200 mm or I can say 0.2 meter. Now the moment of inertia I, that will be equal to Ixx or Iyy, both are same. For a circular section it is pi by 64, diameter raised to 4, diameter is 0.2 raised to 4. So I value comes out to be 7.85 into 10 raised to minus 5 meter raised to 4. So here I have the value of I. Next E is given in the problem and therefore I'll find it is called as flexural rigidity is given by, and that flexural rigidity is the term E into I, and that is E value is given 200 into 10 raised to 6. It is in terms of kilonewton per meter square into I 7.85 into 10 raised to minus 5 meter raised to 4. So here meter square and meter square gets cancelled. So if I calculate this term, therefore EI value comes out to be 15.71 into 10 raised to 3. It is kilonewton meter square. This EI value would be required further in the problem. Now, after we have reached this stage, the next thing would be, since we are solving it by using double integration method, so here I'll say that let there be a section XX at a distance small x from point A, that is the left hand support. So here in the diagram of the beam which is given to us, I am going to assume a section XX which is from point A and it should be far away from point A and very close to point B. So here I am taking this section which is section X. So now here first I have taken the section, next I will write RA RB values. RA was 34 kilonewton, RB 36 kilonewton. Now I am going to take the moment at this section XX because I am using the double integration method and which is also called as Macaulay's method. So after I have taken a section, I will say that by double integration or Macaulay's method, we have moment at XX section is equal to EI d square y by dx square is equal to, now this is the term by Macaulay's double integration method, Now we have to be careful. Here we are having UDL only between portion C to D, but while solving it by double integration method, we have to extend the UDL up to any one of the supports. So here I am going to extend this UDL from point D. I am going on extending this up to support B. Now to balance this UDL, which I have taken extra from D to B, I will have UDL under the beam from D to B, so that the effect gets cancelled out. This step we have to follow when we have UDL anywhere in the middle of the section. That is, in the middle of the beam, if we have UDL, we have to extend that UDL up to any one of the support, and to balance that, underneath the beam we have to add another UDL up to the extended portion. That is, here I have extended the UDL from D to B. So to balance that, we have another UDL which is at the bottom of the beam, and that UDL will also have the same intensity as the previous one, which is having 10 kilonewton per meter. So now we can easily apply the moments. The first thing is, when I am taking the moment, here again I'll take clockwise moment positive and anti-clockwise moment negative. So the first thing is RA, and it produces clockwise moment, so the distance is, it is RA into X. Next we have 20, which produces anti-clockwise moment, and it is at a distance, the distance between 20 kilonewton and XX section is X minus 1. So it is minus 20 into X minus 1, because X minus 1 is the distance between 20 kilonewton and section XX. Next, this 30 kilonewton, I am taking the point load first. 30 kilonewton, the distance between this and XX section is X minus 4, and it produces anti-clockwise moment, minus 30 into X minus 4. Now is the term of the UDL. UDL 10 kilonewton per meter. Initially it was from C to D. Now we have extended this from C to B. So I have to take this entire length, and this is 10 into X minus 1, and that will produce an anti-clockwise moment. So it is minus 10 into X minus 1. That gives me the value of UDL into point, which becomes point load. Now this point load will act at exactly half of X minus 1. So when I am taking the moment, it comes in anti-clockwise direction, so negative. So this becomes minus 10 X minus 1 whole square by 2. Similarly, the UDL which is there at the bottom. Now if I consider this UDL, it is producing clockwise moment. So plus, intensity is same, 10. Now the distance of this is, it is acting at X minus 3. X minus 3 is the distance of this UDL. So it is into X minus 3. This gives me the value of UDL converted into point load, and it is acting at half of X minus 3. So here this becomes X minus 3 square, because it is acting at half of X minus 3. Now once I have reached here, I'll put the value of RA. RA was 34. So 34 into X minus 20 into X minus 1 minus 30 into X minus 4, then minus 10 by 2 X minus 1 whole square plus 10 by 2 X minus 3 whole square. Next, once I have reached here, now I am going to integrate this equation once. So therefore, integrating once, we get, because it is the double integration method, so we have to go on integrating it. We will integrate it twice. So first I am integrating it for the first time. So EI will remain as it is, because it is constant. D square y by dx square, that will be dy by dx. 34x, integration is 34 x square by 2 plus C1 is the constant of integration, then minus 20 into x minus 1 whole square by 2 minus 30 x minus 4 whole square by 2. I am integrating this. minus 10 by 2, x minus 1 square, so integration becomes x minus 1 whole cube by 3 plus 10 by 2, integration of x minus 3 whole square is x minus 3 whole cube by 3. Now I'll again write it in a more simplified form. So that will be EI dy by dx is equal to 34 by 2 x square plus c1, then minus 20 by 2 x minus 1 whole square minus 30 by 2 x minus 4 whole square minus 10 by, now in the denominator we have 2 into 3, that becomes 6, so 10 by 6 x minus 1 whole cube, then plus again we have 10 by 6 x minus 3 whole cube. So this I will keep it as my equation number 1. Now I have integrated once and I have got this equation. Here we have dy by dx. This is called as the slope, and from this we will get the slope equation. Now I will integrate again the slope equation. Therefore integrating again we get, here we have EI, it will remain as it is, dy by dx, that is equal to y, then 34 by 2 x square, integration is x cube by 3 plus c1, integration is c1 into x. Since I am integrating it twice, so another constant which is c2, minus 20 by 2, this is x minus 1 square, so integration is x minus 1 whole cube divided by 3 minus 30 by 2 x minus 4 square, so x minus 4 cube divided by 3 minus 10 by 6 x minus 1 whole cube, so that is x minus 1 raised to the power 4 divided by 4 plus 10 by 6 x minus 3 raised to the power 4 divided by 4. I'll simplify this. So we have EI into y is equal to 34 by 6 x cube plus c1 into x plus c2 minus 20 by 6 x minus 1 cube minus 30 by 6 x minus 4 whole cube minus 10 by 6 into 4, that is 24, x minus 1 raised to 4 plus 10 by 6 into 4 is 24, x minus 3 raised to the power 4. Now I'll keep this as equation number 2. Now after getting equation 1 and equation 2, we need to find the constants. So I'll say that therefore in order to calculate the constants applying boundary conditions, so now applying the boundary conditions, here when I am applying the boundary conditions, we need to put the values in the equation of y, which is the deflection equation. So here I'll say that the first boundary condition will be when the distance x is 0, there is no deflection, so deflection is 0. So here the first boundary condition is at x is equal to 0, the deflection y is 0, and the second boundary condition is at x is equal to the total length, which is 5 meter, that is at point B. Again at point B the deflection y is 0. So at x is equal to 5 meter, y is equal to 0. So here I am going to apply the boundary conditions one by one. So I'll say that therefore put first boundary condition in equation number 2, because we want deflection. Now here at x is equal to 0, y is 0, this is the first condition. So if I put y is equal to 0, left hand side is 0, is equal to, on right hand side this term will become 0 plus c1 into x, x is 0 plus c2. We have to take it only up to c2, that is the first boundary condition. So here I'll say that from the first boundary condition c2 comes out to be 0. Next I'll say that put second boundary condition in equation number second. So at the second boundary condition we have at x is equal to 5 meter, y is 0. So again left hand side is 0. On the right hand side we have 34 by x as it is. X is 5 meter, so 5 cube plus c1 into 5 plus c2 is 0 minus 20 by 6. Then we have x minus 1, that is 5 minus 1 whole cube minus 30 by 6, 30 by 6, x which is 5 minus 4 cube, then minus 10 by 24, x minus 5, x minus 1 which is 5 minus 1 raised to the power 4 plus 10 by 24. Then at last we have x, that is x minus 3, 5 minus 3 raised to the power 4. So on calculating this and simplifying here, I'll get my answer of C1, which comes out to be C1 value. It is here, this value is minus 78. That is, I have found out the value of C1. Now after getting the value of C1, if we see in the question, they had only asked us to calculate the deflections, not the slope. So I will be putting the value of constant in the deflection equation because we have to find only deflections. So no need of slope. So here I'll say that deflection we are getting in equation number second. So here we need to put C1, C2 values. So I'll say that therefore put C1 and C2 in equation number second. So I am putting the values in equation second. So in equation second, on the left hand side we have EI into Y, and it is equal to 34 by 6 x cube plus C1 into x. C1 is minus 78, so minus 78 into x. C2 is 0, so no need to write that term. I'll copy the remaining terms as it is. Now here we have this equation in which we have put C1, C2 values. So therefore I'll say that equation number 3 gives deflection equation, and from this deflection at any given distance in the beam can be calculated. So here we have the deflection equation in which we can calculate the deflection at any given distance because x is the variable here. And now if we look into the question, the first thing which is they have asked is to calculate the deflection, to find the deflection at B, C and D. So first at B, when we are trying to find the deflection, the distance we have to consider is from point A up to B, it is 5. So I have to keep x is equal to 5 meter, and there the deflection value, it is 0 that we have seen in the boundary condition. So I'll say that the first thing is therefore y at point B is equal to 0. So this will be the first answer, and this is 0 because since it is simply supported beam. Next, we have to find the deflection at point C, that is x is equal to 1 meter. So therefore, at x is equal to 1 meter, put in equation 3. So once I put the value here, that will be therefore EI into y, it is 34 by 6, x is 1, so 1 cube will remain 1, minus 78 into x, that is 78 into 1 will remain as it is. Next, if I put 1 here, that becomes 1 minus 1 is 0, so this term is neglected. Next, we have minus 30 by 6 into x minus 4, that is 1 minus 4 whole cube, minus 10 by 24. Here again we have 1 minus 1, so this term gets eliminated. At last we have, so here this term is eliminated, it is into 0, plus 10 by 24 into 1 minus 3 raised to the power 4. Now on simplifying this, on calculation, here we have therefore EI into y is equal to, now if we see this, the first term is 34 by 6, so that is 5.67. Next we have minus 78, then it is 1 minus 4 cube divided by this term, so we have 1 minus 4 cube into 30 by 6, so that is minus 135. Then we have plus, the last term is 6.67. So on adding them, we are going to get y, and this y is at point C. So yc will be equal to, if I go on simplifying this, it is 69.34, and I will send EI term in the denominator here. So now here I will put the value of EI because it is given in the problem. So we have found out EI was 15.71 into 10 raised to 3. So 69.34 divided by 15.71 into 10 raised to 3, and that gives me the answer of y suffix c as 4.41 into 10 raised to minus 3 meter, or I can say that it is 4.41 mm. So this is my answer second, that is, here I have calculated the deflection at point C. Next, I'll calculate the deflection given in the problem at point D. So at point D, the distance is 3 meter, so I'll say that therefore put x is equal to 3 meter in equation number 3. So we have this equation 3. Here I'll put the value. So EI into y, since we want to find it at point D, so it is y suffix d is equal to, here we have 34 by 6 x cube, so it is 3 cube minus 78x, so it is 78 into 3, then minus 20 by 6, here we have 3 minus 1 cube minus 30 by 6, we have 3 minus 4 cube, then minus 10 by 24, 3 minus 1 raised to the power 4, and at last we have plus 10 by 24, this is 3 minus 3, so it becomes 0, so there is no need of the last term. So here I'll simplify this. Therefore, EI y suffix d is equal to, the first term is 153. Next we have 78 into 3, that is 234. Then we have 3 minus 1, which is 2. So 2 cube into 20 divided by 6, we have 26.67, minus 3 minus 4, which is minus 1, cube, which is again minus 1, into 30 divided by 6, so that is minus 5. Then minus 3 minus 1 raised to the power 4, that is 2 raised to power 4, into 10 divided by 24, so that is 6.67. Now on simplifying this, I'll get the answer as EI y suffix d is equal to, it comes out to be minus 109.34. Therefore, here I'll keep this as it is, shifting EI. Now putting the value of EI, which we have found out previously, that was 15.71 into 10 raised to 3. So my answer of deflection at point D comes out to be minus 6.96 into 10 raised to minus 3 meter, or I can say 6.96 mm. So this is the third answer. Now if we see in the problem, we have found out deflections at point A, we know it is 0, at B it is 0, at B, then at C and D also we have found out. Now let us try to add one thing in the problem, that is find the deflection even at point E, which is not asked, but I am adding this. So here I'll say that also find deflection at point E. So to calculate the deflection at point E, now its distance is 4 meter from A, so x will be 4 meter. So at x is equal to 4 meter, put in equation 3. So in the third equation, now I'll put the value of x as 4 meter. In the third equation, we have EI into y. I want to find at E, so suffix E. Then 34 by 6 into x cube. So 34 by 6, x is 4, 4 cube. Then minus 78 into x, so 78 into 4. Then minus 20 by 6 into x minus 1 whole cube, so 4 minus 1 whole cube, minus 30 by 6. Now here we have x minus 4, that is 4 minus 4, so it becomes 0, no need of this term. Then we have minus 10 by 24, x minus 1 raised to the power 4, so 4 minus 1 raised to the power 4, plus 10 by 24, 4 minus 3 raised to the power 4. So now I am going to write these terms in a more simplified manner. So therefore EI into y suffix E, that is equal to 4 cube into 34 divided by 6, that is 362.67, minus 78 into 4, that is the next term, 312, then minus the remaining part. Then we have 33.75. At last we have 0.4166. So therefore EI y suffix E will come out to be, I am adding all the terms here, so that answer is minus 72.66. Now I want y suffix E So shifting EI in the denominator, EI is 15.71 into 10 raised to 3. So therefore the deflection at point E, that comes out to be minus 4.63 into 10 raised to minus 3 meter, or we can say minus 4.63 mm. And since I am getting this deflection sign as negative, it means the deflection is in downward direction. Previously also y suffix d was negative, it means it is in the downward direction. So once we have found out all the deflections, we can say that the problem has been completed.